So you can treat these as notes if you wish. As always, I don't encourage you to write every word down. Your note should be a summary for you. It should be personalized. What happened in class? Alrighty, so let's talk a little bit about friction. We're going to calculate the coefficient of friction, which you might remember, and solve problems on flat and inclined surfaces involving friction. So in grade 11, you would have done a little bit of the mu stuff. So we're going to take that sort of one step further today. So quick kind of refresher here about friction. So friction is a force that resists motion, and it involves objects that are in contact with each other. There must be contact. Right? And air resistance is a type of friction. Water resistance is a type of friction because the air molecules or the water molecules are in contact with the object, right? And I wouldn't bother writing it down. Some causes of friction, things that cause friction. By the way, the handout package that you got Monday sort of is where these notes came from. So I mean, you might be able to find them and just highlight it as you go through if you want. This is sort of the summary of that. Is it the first page of the package? Yeah. Okay. So, cause of friction in an object will deform a surface and vice versa. So, in other words, you know, my laptop or a book sitting on a table will actually create a little sort of impression, a little, I guess, a depression in the table. A plowing force is required to move the object over the deformations, or in fact, I guess it's uphill actually on the far side. Irregularities interlock and offer resistance to movement. Obviously, they are not smooth, right? Here's the table. Here's the book, right? You know, on a microscopic level, and sort of they're all sort of these little sort of humps and bumps kind of thing. When you're sanding in wood shop, right, with your sandpaper, making it smooth, you're actually taking those off and smoothing them down. Friction is not overly well understood. There's still some issues there. Some people believe that intermolecular forces are at play as well, that the molecules are attracted to each other, and that's cause of friction too. You should know the difference between starting friction, which is the maximum frictional force between stationary objects. So when something is stationary at rest, almost, yeah. When something is at rest, it has its maximum frictional force between stationary objects. And when it's moving, then we call that sliding friction. That is the frictional force between objects that are sliding with respect to each other. Rolling friction is a bit more complicated. For now, and here, just assume everything is sliding, even if it's rolling. Okay? I was at a workshop once and they talked about how rolling friction actually is a type of stationary friction because the wheel is at rest for that moment, and then as it turns, the next portion of the wheel is at rest. So a little more complicated. So starting friction, sliding friction. Other words for them are, this would be static, and this one would be kinetic. So kinetic friction or static friction. All right, some properties of friction. Friction acts parallel to the surfaces that are in contact and in the direction opposite to the motion of the object or to the net force tending to produce such motion. So there's lots in that one there. It's parallel to the surface and is in direction opposite to the motion or to the net force tending to produce such motion. So in other words, if it's moving, it's opposite the direction. But what if it's not moving? What if I just push on a big desk that's attached to the ground here? Well, friction is opposite to the attempted motion, right? Or to the net force tending to produce or attempting to produce such motion. So there doesn't have to be motion for there to be friction, I guess is what I'm saying. Friction depends on the nature of the materials in contact and the smoothness of their surfaces. Obviously, the smoother the surfaces are, the less friction there is. Up to a point, then there becomes a point where they're so smooth that they're so close together, and there is theories that intermolecular forces are at play. It even can create a bit of a vacuum as well. So you can get things that are so smooth that there is a significant amount of friction. Glass on glass is kind of one sort of approximation to that. But generally, the smoother the objects, the less friction there is. Sliding friction is less than or equal to starting friction. Friction is practically independent of the area of contact, and the way that I always explain that is if you take a regular textbook and you've got it flat kind of thing, and I'm going to draw this for the people that are out there watching on YouTube, right? If you've got it flat on the table, you've got a certain amount of surface area, but if you stand it up on end, right? Cool, that's not right. If you stand it up on end, there's obviously less surface area, but what about the weight of the object, or the mass? The mass of the object is exactly the same, right? So no matter whether it's flat, like on the left there, or if it's upright on the right, the friction is the same, because the mass of the object is really what matters, which creates the weight force. That's, of course, providing that both sides of the book are the same sort of material. Starting or sliding friction is directly proportional to the force pressing the two surfaces together. Most of the time, that's equal to the weight force, right? Most of the time, the weight force and the normal force are equal to each other. When you get onto ramps and other things like that, then you get some issues. So we'll deal with those individually. But generally, starting or sliding friction is directly proportional to the force pressing the two surfaces together, usually caused by the mass, the weight force. Okay, remember this fine fellow from grade 11? Did you all see it in grade 11? I think so, right? Even the class that missed me for a few months. You don't remember, John? I blocked it out? I took those out, yeah. Fair enough. So mu is equal to FF over Fn. Now, I've been told by someone with Greek heritage that it's actually pronounced me. But everywhere I looked on the internet, I spent some time actually, not me. Everywhere that I found, all the scientists pronounce it mu. So, I don't know. Who am I supposed to believe? I'm going to say mu because that's what I've learned. Yeah. So basically, it's that funny-looking U with the tail out front. So it's friction force divided by normal force. Shall we do an example or two? I don't think. Now, in that package, do you guys have example questions? I should point out, Shady, can I just borrow yours for a second? I should point out that in the package there, at the bottom there, just underneath the skier, there's some coefficients of friction down there. You may need those at some point. You will notice that wood on wood, sliding friction is about what? 0.3, and we will be determining that in the very near future. We're going to take a block of wood and actually slide across another block of wood and find out what the coefficient of friction is. And you should get something around 0.3. You will get close to 0.3 when we actually do it. Okay, so let's do you have those example questions? I think you do, right, Katie? Excellent, okay. So here we go. An object has a mass of 10 kilograms. A force of 100 newtons is applied to it. The coefficient of friction between the two surfaces is 0.25. Determine the object's acceleration. All right, well, let's start off with a free body diagram. This is 10 kilos. We have a weight force, and we have a normal force. And a applied force of 100 newtons is applied to it. Fa. Is there friction? It says there's a coefficient of friction, so that says that there is friction. Determine the object's acceleration. Now, we don't actually know what the size of that frictional force is, but as soon as it's asked for the object's acceleration, that sort of implies that there's going to be one, right? And we're using this to solve the question. We're not sort of demonstrating with it, I guess, or something like that. So it doesn't really matter how much the lengths are particularly. Okay, so the first thing we know is we want to find the object's acceleration. So to get that, we're going to need, to get to acceleration, we're going to need the net force, right? And the net force is made up of the applied force plus the friction force. And we know the applied force, but we don't know the friction force. So we've got to get friction force, which we're going to use our new old friend mu equals FF over Fn, but we don't have Fn yet, do we? How am I going to get Fn? Mass times gravity. So let's start with that. Fw is equal to mass times gravity. 10 times, now should I use minus 9.8? You can. Yeah, we're going to change it. You're right. Minus 98 is our weight force. Therefore, the normal force is 98. I guess to be technically correct, we should leave it as negative and then change it to positive. And now that I have my normal force, I can get my friction force by using mu equals Ff over Fn. 0.25 is equal to friction force over that 98. You probably have answers for these somewhere. I'll live on the edge and I'll do the problem as we go. $24.5. Friction force is 24.5 newtons. And now that I got the friction force, that with my FA will give me my F net. You got to admit, if I showed this to grade 11s, their minds would explode, right? Be too much, right? But you've come that far, right? You've become better at it. Yeah. Well, yeah. Yeah. But after about 4 or 5 days of it, Connor, right? This is like the first example, right? This is example 1. With you guys, that would have been example 5. Yeah. Right you are. Okay, so here the applied force is 100. Now, what direction is the 24.5? Like, it's not negative here, is it? So somewhere between there and there, you have to make it negative because it's going left, right? You have to manually do that. Subtract it from 100.
So how did you cut
Well, then you'd get 124.5, right? Like, it has to be negative. It has to reduce that applied force mark, right? I mean, if you... What do you mean?
100 subtract.
Yeah, I like to write it as 100 plus minus 24.5 because it strengthens that idea of you're adding the vectors together and that the friction force is negative. Okay? Okay, so now F net is equal to MA, 75.5. And you're simply going to divide by 10. 7.55 meters per second squared. Oh, Josh, what is with me in names today?
That like
Squiggle?
yeah, that squiggle in the middle.
Here?
No, up on the left, like the formula.
Huh?
What is
FW equals mg?
on the right? Yeah, like right there.
Mu equals FF over Fn.
Mu?
Yeah.
Yeah, I know, but I don't know what mu.
Oh,
It's the coefficient of friction.
coefficient of sliding friction, right
It's
there.
that little.
That little thing right there, yeah.
Okay.
Like a crying.
The crying U, yes. Too much physics homework. The crying U.
Crying.
All right, so let's apply this now to a ramp. So on whatever day that was it Monday?
Monday.
We talked about ramps, right? Let's see what happens here. So an object has a mass of 10 kilograms, placed on a ramp with an angle of 35 degrees. The coefficient of friction between the two surfaces is 0.15. Determine the object's acceleration down the ramp. Okay, so I'm going to do this, FW. Now remember we've got, let's do this better. FW. Remember we've got these components here, right? And this one is FD, and this one we are labeling as FN. Technically, it's the component of gravity that is perpendicular to the ramp surface. And it's equal and opposite to this normal force, right? So we sort of simplify things a little bit. And this FD I like to draw here, really. Okay? And which way would friction be? It'd be like this, right? The friction would be opposite like that. And if the FD was more than the friction force, then it would slide down the ramp. And it says determine the object acceleration, so we're going to make that assumption that that's actually the case, right? Okay, so how do I find FD and FF? Well, FD, to determine the object acceleration, the first thing I'm going to need is my net force. And the net force is going to be made up of the FD and the FF. FD we have a formula for, mg sine theta. FF we have a formula for, but it's mu equals FF over Fn, but we don't have Fn, do we? But we do have a formula for Fn, don't we? Fn is equal to mg cos theta. So let's do those two formulas right there. FD is equal to mg sine theta. We learned that on Monday. So that's going to be 10 times 9.8 times the sine of 35. $56.2. And that number, of course, is always going to be less than the weight force. Fn is mg cos theta. 10 times 9.8 times the cosine of 35. $80.3. So I've got FD and Fn. Now, before I can use that Fn, I have to convert that to friction force. So mu FF over Fn. What was the coefficient here? 0.15. .05. Whoopsie. Right, now that we got that, now we can go to the net force. .2, we'll say, and throw that back into Fnet equals MA. And of course, once you got the acceleration, you can find out things like how long does it take to get to the bottom of the ramp and how fast it's going and all that stuff. Are we good with all that? Yeah? Okay, last one. This one's a bit of a challenge. We did, I think, touch briefly on this in grade 11, but let's have another look at this. Here we have a box weighing 40 kilograms pulled along a level floor at a constant speed. Why am I pausing? That's important. It means that the cell acceleration is 0, which means that the forces are equal or balanced. By a rope that makes an angle with 30 degrees with the floor as shown. If the force on the rope is 260 newtons, What is the horizontal component? And remember now that I'm changing this to FAX. What is the normal force? And what is the coefficient of sliding friction? Okay, so let's draw a picture here. We're going to call that FA. And then I'm going to put here in red, I'm going to call this FAX, the horizontal, the X component of the applied force. And that's going to make this one here in blue FAY, the Y component of the applied force. Okay? Now we also have weight force down, and we also have a normal force up. And here's where things start to get a little complicated. I guess we also have a friction force here. Suddenly this is getting full of force. All of the forces are balanced. All of the X and the Y forces are balanced. How do I know that? Because it's at a constant speed. Okay, so that means, therefore, that the FAX is equal to the FF, right? But it also means that the sum of all the downward forces is equal to the sum of all the upwards. And there's two upwards, isn't there, right? So there's various ways to show this, and this is sort of the new way that I think I'm going to do it because it leads into some other things a little bit down the road here. So I'm going to say that 0 is equal to, now let's do it the other way. Let's do it this way. Let's say that FAY plus FN plus FW equals 0. Why 0? It's not accelerating vertically, is it? Right? The net Y forces are balanced. Okay? So to get the normal force, I'm going to need to know the weight force, and I'm going to need to know the Y component. Right? Okay, so let's go ahead and find those. So the weight force is easy. It's just mass times gravity. 40 times minus 9.8. $392 newtons. The Y component is opposite, right? So it's going to be, how do I find this here? We have this angle of 30 degrees. It's going to be sine, right? Opposite. So FAY is going to be equal to FA sine 30. So that's 260. I guess this should really be sine theta. This is 260 sine 30. $130. Okay, so really, I should rewrite this. I realize you guys can't do this. How about I do this? So the FAY is 130. Now, do I need to worry about directions here? Do I need to worry about signs, positive or negatives? Yeah. You betcha I do. So this FW really should be negative, right? So the 130 is up, it's positive, plus the normal force, plus the weight force, which is plus a minus 392, is all equal to 0. Right? So now I'm going to isolate Fn by taking those to the other side. The minus 392 goes to the other side and becomes plus 392. Or if you want to think about it, you add 392 to both sides. And then you got 130 here. We're going to take away. If you take it away from the left, you got to take it away from the right to be fair. 262. So the normal force, what has happened here? Fn is reduced. It's less than what it would be normally, pun intended. Normally, the weight force is equal to the weight force, 392, but this time it's reduced. How come? Because you're lifting up. When you lift up, you reduce friction, right? If someone's trying to slide something heavy, if you lift, it's going to make it easier to slide. So that Fn is reduced. Now, I don't even remember what I guess this is what I was supposed to find it, right? I haven't even got part A yet. I went and did part B, didn't I? I'll just do what students do, just call this part A. Yeah, I know. FAX is just going to be FA cos theta. I guess I should have read the question. 260, the cosine of 30. $225. And now, what is the coefficient of sliding friction? Mu equals FF over Fn. We don't have an FF yet, do we? But you'll remember from a few minutes ago, I said that the FAX has to equal the FF, right? How come? Constant speed. Right? So therefore, you guys know 3 dots in a triangle means therefore. Therefore, the friction force would be 225. Technically, it's negative 225 because it's to the left. And now you can use that in part C. Mu equals FF over Fn. So 225. There is no negative in this here. It's just a ratio. 225 over 262. And you get 0.86. What are the units? What are the units for mu? There is none. Exactly. How come? Because it's a force over a force, newtons over newtons, right? And you might remember from grade 11 too that the mu value is most of the time a decimal less than 1, Martin, right? If it's greater than 1, either I've made a mistake or you've made a mistake or it's really rough, right? But generally less than 1. 0.86 is considerably high, right? Like rubber tire on a road is like 0.4 or 0.5, you know, and that's going to stop pretty quick. So, okay, is there a problem pack at the end of that package there?
Yeah.
Okay, so you should spend some time on those. Can't you see that, Katie? Okay, so there are questions there. Oh, there's 3 questions that are starred. You should, at the very least, that's the minimum that you should do. 3, 6, and 9. There's a code there, but there's no link. Oh, there's answers on the back. If you want, I can post the answers to Schoology. Those of you that were here yesterday, I handed out an answer key to the test, and I also posted it to Schoology so you can see the answers to that test. We made a decision with that question. Which one was it, you guys? What's the number, though?
6.
6, the truck one, where the truck's passing. Turns out part C is worth like 5 marks, so I've agreed that it's a little unfair. There was only 2 people in the class that got it right. There was 1 person that got 4 or 5, I think, maybe. So I'm going to redo that question. I'm going to make up a new one for that one, and we'll come up with a time that we can rewrite just that one question. Okay? I'm going to try to spend some time today coming up with an example.
Aye, Captain.
Okay. So you got some time to work? I'm hoping to move on tomorrow too.